So good afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome Professor Fèlix Llovell. He currently holds the position of Associate Professor and Secretary of the Department of Chemical Engineering at the Universidad Rovira and Virgilia. His research interests include the development, use, and improvement of molecular modeling tools for practical applications to complex systems of industrial interest, with particular focus on the physicochemical characterization of new solvents, development and improvement of molecular-based equation of state, renormalization group theory, applied to the study of the critical region of fluids, application of density functional theories for the study of interface, development of predictive methodology for the study of transport properties, and such. He's the author of 80 referred journal publications that have been cited almost 2,500 times. And welcome, Professor Llovell. Thank you so much for being here. Please feel free to start your presentation.
Okay, thank you. Thank you very much. It's really a pleasure to be here. I'm just going first to share my screen to be sure that everything is okay. So let's just okay. So apparently you should be seeing my screen. Well, as I was saying, first of all, I'd like to say thank you very much to Professor Tavares and all the group in Atoms for inviting me to this seminar. I've been seeing some of the previous seminars and some of the great speakers you have had, and it's really an honor to be part of this team. So thank you very much, and also thank you for this very nice introduction. Today, I thought about talking on one of the latest areas of my research, which is focused on studying and understanding a new class of solvents, which are called Diplotactic Solvents. Of course, from a computational perspective, which is the main focus of my research, as it was mentioned right now. And the idea is I know there are very great speakers in the area, great experts, and you have people who have already talked, such as Professor Joe Coutinho, for instance, and some others. But the idea is to give you a little bit of overview of some of the applications we have been working and trying to get some insight. Just before starting, I just briefly mentioned that during the last 5 years until 2020, I was working in another institution at Institut Químic de Sarrià in Barcelona, in University Ramon Llull. And since last year, I work, as mentioned by Yuri, as an associate professor at the Chemical Engineering Department at the University Rovira and Virgilia in Tarragona. And I all invite you to come once this pandemic is let's say at least stopping a little bit. I really welcome you all. It's a very nice place. And since 2017, I am working in the engineering and simulation of environmental processes research group, a group that I created when I was at the former institution. And our goal is to provide responses to the current society challenges, talking about climate change, water scarcity, and population growing. I guess that you all have seen the latest news on the IPCC report and how dramatic the situation is. And the idea is to combine different skills to work towards sustainable solutions. Of course, there are different areas of research, one more devoted to water treatment, another one more on greenhouse gas treatment, and another one more in alternative ways to produce energy from a sustainable manner. But all of them are merged, of course, in one experimental site, but also in a process of molecular modeling site. And this is, let's say, where my expertise is and where I am working to focus my talk. Today, as I mentioned, the idea is to talk in particular about this type of new solvents that have appeared such an explosion, and there are many people talking about them. What are these days? So I'm just trying to first of all talk a little bit about the fundamentals, and then I will explain how we can model them, and we'll show a couple of applications. So diplotactic solvents are, as mentioned, an emerging class of mixtures which are characterized by significant depressions in melting points at the eutectic composition compared to those of the pure constituent components. So the idea is that we have a mixture, and this is the first point that we want to highlight. We have a mixture, we don't have even if they are talked as a single solvent, they are always a mixture of solvents where there is a combination of a hydrogen bond donor and a hydrogen bond acceptor. Of course, there are many different types of diplotactic solvents according to the type of donor and the type of acceptor. But the idea is that the combination of both produces a depression on the freezing point. And this depression is related to the strength of interaction between the two components, which typically create a strong network of interactions, typically called hydrogen bonding interactions, although we will later see how there are many different types of interactions occurring in the system. With this definition, we could understand that diplotactic solvents are just an eutectic mixture, as this is shown in this diagram here in the left side of the image, just a typical solid-liquid equilibrium line. But here we have to pose a crucial difference, which has been pointed out by several authors. Let's go to particularize the definition of diplotactic solvents. Although there is not a clear definition, diplotactic solvents have to be understood as mixtures whose melting point, when they are at a different composition, at a particular composition, is lower than that of the ideal liquid mixture. Because normal ideal liquid mixtures already exhibit a depression in the melting point when they are mixed. Here, as an example, we can see the red line, which would represent an ideal liquid mixture whose solid-liquid equilibria could be represented just from the pure component properties. That's the enthalpy of fusion of each one of the two compounds and the melting temperature of each one of the two pure compounds. The difference between a normal ideal liquid mixture and a diplotactic solvent is that there is an important deviation which still decreases significantly the melting point. This is because we have an activity coefficient in the liquid phase that produces this depression due to these strong interactions between the two components. At the end, the thermodynamics of the system will give us the solution. Basically, this is the difference between the chemical potential of the solid and the liquid, which depends, as mentioned, on the pure properties, pure component properties, but this activity coefficient will produce this decrease in the melting point. It is important just to point out this difference in order to avoid confusion when defining a diplotactic solvent. In any case, the most important thing is not the definition, but what it is going to cause this depression. In particular, the most interesting thing is that this depression will provide a higher range of compositions where the solvent will be liquid, and then it will be practical for different solvent applications. As far as we reduce the temperature, this is like ionic liquids in some manner, we have more opportunities to use these compounds as possible solvents for many different applications. The most common and well-known diplotactic solvent was developed already 18 years ago in 2003, and it is polychloride urea at a proportion of 1:2. This was discovered by Abbott and co-workers, and it is impressive to see how the melting point can decrease from 575 Kelvin till 285 Kelvin at a 2:1 proportion. Here you can see the melting point of choline chloride and the melting point of urea. In this case, we can see how at different compositions the mixture is solid And at the particular eutectic composition, the mixture is liquid at 12 degrees Celsius. This cheap system, done with very cheap compounds, has been applied to biomass treatment processing, protein folding stability, synthesis of nanoparticles, among many other processes. Also, another point that it is important to mention is that there is not a particular proportion where the eutectic composition will appear. It is commonly seen in the literature that we see 1-1, 1-2, 2-1, 1-3, but it may appear at other proportions because at the end, it's two melting lines that are joining at a particular point. And it is not necessary to have a particular proportion to get an eutectic mixture. Also, more importantly, it is not extremely necessary to work at the lowest temperature. It is important to work in a range of composition where the mixture is a liquid. That's the important thing, to be liquid in the area of the operating temperatures of our process. Here, I'm just showing some of the possible hydrogen bond donors and hydrogen bond acceptors. There are different types and families of diplotactic solvents, but most applications have been studied with type 3, where the hydrogen bond acceptor is typically a salt, and the hydrogen bond donor is typically a carboxylic acid or a glycol. There are, of course, other types of systems, but mostly these two. Here you can see that there are thousands of combinations, but not all of them will provide a death. They should be studied one by one. And even if they are very advantageous because most of these compounds, they're cheap, non-toxic, and non-reactive with water, they have to be studied one by one to really understand their properties, requiring an intensive experimental work. Here, I'm just highlighting some of the particular applications where diplotactic solvents are being studied, and in some cases, they already have been used. As you can see, the amount of possibilities is enormous. So these are becoming very attractive for researchers. We can see this in the exponential growth that diplotactic solvents have experienced in the last years. This is just a statistic taken putting the words diplotactic solvents in the Web of Science. And you can see that there is an exponential amount of work published on the topic. Then the question that comes to our mind is, if we have many different options and we need to understand the physicochemical behavior, how do we relate the physicochemical properties and the understanding of the physicochemical properties to the selection of a particular application, and how these physicochemical properties are related to the physics behind the two compounds joining at a certain composition? Here I'm just highlighting some of the properties that should be known in order to drive their use for a possible application. You can see that as people who work in a group on molecular simulation and apply thermodynamics, some of them are not easy to obtain with thermodynamic models. So the question is, do we have theoretical tools able to provide responses and being capable to design a death ad hoc? Because we need to combine our experimental work with computational modeling so as to reduce the amount of possible combinations. Here, I just want to highlight how complex these type of molecules can be. The most well-known molecule, choline chloride with urea, is one of the most complex to understand. DFT calculations in the work performed by Patricia Hunt and co-workers have revealed more than 10 different interactions that are important in terms of hydrogen bonding. When we talk about hydrogen bonding, we include many different types of hydrogen bonding that can be related to ionic interactions, double ionic interactions, and neutral interactions. In this sense, we could expect that if we have a look at the choline chloride urea molecule, we would expect that the most important interaction would be that of the chloride with the NH group of urea. However, these DFT calculations revealed that this is not by far the most important interaction. In this figure, we can see how the different types of hydrogen bonding appear in this molecule and how strong the energy of the interaction is. In this regard, we can relate the occurrence with the energy, and we can describe this type of interactions such as strong, moderate, and weak. And we can see that by far, the strongest interaction, which occurs more often, is that one between the urea molecule and the choline molecule. In this particular case, is the hydroxyl of the chloride, the OH of the chloride, which is interacting with the oxygen of the urea here. This is the most important bond. We can also identify another one, which is still stronger than the one between urea and chloride. Here, we can see that the carbons accompanying the choline can also interact with this oxygen. Also, it is important to notice that, as mentioned, there are different types of bonds related to the type of nature they have, doubly ionic, or neutral. There are still two other effects that are important. In this case, only related to the choline chloride molecule without urea. One related to the chloride action with the OH, and another one related to the hydrogens with the chlorides, the famous tripodal arrangement of the choline chloride molecule. I'm just highlighting these images to let you know how complicated it can be to describe and has an accurate thermodynamic model to understand what it is going behind a molecule such as choline chloride and urea, which apparently looks like an easy system. For this purpose, it is important to consider the different multi-scale approaches that can provide insight and solutions to industrial problems. Of course, if we need to understand what it is going on at a deeper scale, we have to move towards ab initio calculations or maybe molecular dynamic simulations, which will give us basic information on the molecule and will be capable to identify what are the main interactions occurring in the system, as shown in the previous slide. However, this information can be very useful to build a coarse-grained method based on SAS or other equations of state that can provide a fast calculation with a reasonable degree of structural information. This type of equations can be later applied for process scale for the pre-design of an operation unit, which is a need required by the companies. In this slide, I'm just showing the increasing interest in the description of death in terms of computational studies, although most of them are still in a preliminary stage. In a paper that we published last year, we could see how different types of methods have been used to model diplotactic solvents. We can see there is a quite balanced equilibrium between what we would call empirical models based on correlations or machine learning, which is an increasing field of interest, towards classical thermodynamic methods using classical equations of state, activity, coefficient models, or group contribution approaches, statistical thermodynamics based on molecular simulations or molecular-based equations of state, and quantum chemistry, which can be related to COSMOS and other type of studies related to quantum calculations. In this regard, I just want to highlight some examples before going to particular applications. First of all, I just want to highlight a simple but effective approach that was recently published by Rita Duarte and Sona Raisi, where these co-workers, they studied a model of diplotactic solvents using a group contribution and an atomic contribution approach, which was based on a large database of experimental data. They provided correlations for densities, refractive indices, heat capacities, speeds of sound, and surface tensions of diplotactic solvents. The idea was just to try to get a database as large as possible and build a correlation based on two terms that were biased through a weight, a particular weight. It was quite an empirical model where the molecular structure was decomposed in predefined groups or atoms. Surprisingly, even if the methodology is relatively simple, the results were very good, obtaining a good description of most molecules. When I'm talking about a good description of the molecules, for those of you who are not familiar with this type of studies, typically you select 70 to 80% of your database to fit your parameters, and then you leave 20 to 30% of your data to test your results. In this case, most of the calculated and tested results were having relatively low deviations, as you can see here in these images. For the density and the refractive indices, the deviations were very low, obtaining the highest deviations in properties such as the heat capacity and the surface tension, also due to the lack of experimental data. This is one of the main disadvantages of this type of studies. They require a large amount of data. Now I'm just moving to another work that was recently also published by some collaborators, by Jose Matias Garrido and Hector Quinteros from Chile, where they performed different molecular simulations of the choline chloride combined with ethylene glycol. This is called the ethylene base. They studied the impact of this molecule in this system when alcohol was added, in particular methanol. How the impact of an alcohol was affecting the death, in order to see how it would affect in the case of a solvent. Here you can see different figures where the blue area represents the normalized occurrence of a bond. And here you can see the main identified bonds. So the most common hydrogen bonds were the hydroxyl group of choline chloride with the oxygen of ethylene glycol, which is this one, and also a self-association between ethylene glycol molecules, the hydroxyl group of ethylene glycol and the oxygen group of ethylene glycol. Here in this first line, we don't have methanol. We have only the death. When we are adding methanol in the system, as you can see here, you can observe how methanol penetrates in the solvatation shell and is competing to form new hydrogen bonds. This can be clearly seen in this image and this image, where the blue colored areas are less intense, because this hydrogen bonding is prevented by the addition of methanol. In terms of physicochemical properties, this is producing a viscosity decrease, which will have an impact in the operation unit of our particular application. This data can be also studied combining molecular simulations and soft approaches. In this figure, we can see how these authors, they studied the fraction of self-association molecules calculated for methanol, ethylene glycol, and choline chloride. They could observe that methanol and choline chloride followed a linear trend. The simulations represent the symbols. Methanol has a quite linear trend with the methanol mole fraction in terms of self-associating molecules of methanol, while also for choline chloride, the trend was not perfectly linear, but quite linear. However, for ethylene glycol, it was noticed that hydrogen bond was not affected up to the addition of 30 to 40% of methanol. As you can see here, the fraction of self-associating molecules in ethylene glycol remained equal, constant, until 40% of methanol. Then there was a rapid decrease because, of course, of the addition of many methanol molecules. As mentioned, this type of studies can provide a lot of information in our system and will give us an idea of what it is occurring in order to design our process. However, one of the most successful studies that can be done is using statistical association fluid theory, which I think it is very well known for the audience. However, as far as this is my main area of expertise, I would like to devote some minutes to talk about it. SAF is a theory based on Bernheim's thermodynamic perturbation theory, and it is an equation built from statistical mechanics concepts. The idea or the main difference with respect to previous equation is the addition of highly direction at association sites that consider effects such as hydrogen bonding. In this regard, the use of a theory that includes a specific term that considers hydrogen bonding interactions should represent an advantage to model molecules that strongly depend on these hydrogen bonding interactions. That seems to be a good framework for this. SAF, as mentioned, calculates from statistical mechanics the total Helmholtz energy of the system as a sum of contributions. At the end, we end up with a coarse-grained approach, where the total Helmholtz energy of the system is built from an ideal term, a segment term representing the monomer-monomer interactions, a chain term that represents the covalent bonds to form chains, and the hydrogen bonding association sites that occur in many systems. The type of reference term depends on the type of equation selected, as there are many different SAF versions. In this particular presentation, I'm highlighting the results obtained with the soft SAF, which uses a Lennard-Jones intermolecular potential to consider the repulsive and dispersive forces, using a term that was fitted to molecular simulation data by Johnson and co-workers. The most important thing is that this way to construct the molecule allows to have a series of molecular parameters that have some sort of physical meaning. At the end, we end up with a number of monomers who have a certain monomer diameter and interact through a particular bounded Waals dispersive energy. And then we have a series of associating sites representing this hydrogen bonding with a particular association energy and volume. These typical parameters are normally fitted to saturated liquid densities and vapor pressures. However, for the particular case of this, as vapor pressures are negligible, I didn't mention that, but vapor pressures are almost zero as ionic liquid, as the case of ionic liquid, typically there are other strategies to fit these parameters. But always they will be, then the density of the liquid will be used. Just for those of you who are not familiar with that, I just highlight a very clear example of the importance of hydrogen bonding effects. This is a model for water, which has 4 association sites, and this is a model for propanol, which has 2 association sites that represent the hydroxyl group in the molecule. We could, of course, discuss a lot on the number of hydrogen bonding sites in water and propanol, but this is not the purpose of this talk. In any case, if both molecules are modeled considering hydrogen bonding, but the hydrogen bonding between water and propanol is not considered, the resulting mixture predicted gives admixture gives a liquid-liquid equilibrium, which is false. This is the experimental data that you can find at atmospheric pressure. It's the temperature density diagram, and you can see that SAF does not provide the right result. Why? Because we are not considering the right physics. We are not including the cross association there is between water and propanol. At the moment we do, and we consider this interaction, we have a good description of the molecule. And here it is also important to repeat the idea that we deal with a cross-grain approach, which has several assumptions before. So some of the results will be at a qualitative stage, and this will have to be considered and always tested either with experimental work or corroborated with atomistic simulations. One of the advantages of using a SAF framework is that the question can be improved in many different manners. This molecular framework allows the addition of many new theories to consider, for instance, the critical region of fluid, the interfacial region of fluids, to specifically treat ion electrostatic interactions or polar effects, or to include the solar phase, a solid phase, and transport properties. There are, here I'm just highlighting some of the improvements that were made during the last 20 years in soft SAF by several coworkers. In particular, I just mentioned, because I will show some graphics, the idea of the free volume theory as an additional theory included to describe transport properties, and in particular, the viscosity of fluids. Viscosity in Diplotactic solvents remains a crucial and key aspect, considering that we are dealing with mixtures that whose strong network of interactions could cause an increase of the viscosity of the system. So it is important to have a tool capable to describe viscosities. And in this case, we use the free volume theory coupled into soft SAF. The free volume theory just assumes that the viscosity is related on the expression of the Dipole model, which was already developed many years ago. So it is directly related to the microstructure of the fluid and the density of the system, and also about a second idea that was also demonstrated, which is the Doolittle's model of a theory that was demonstrated in the 50s, that says that the dense fluid is dependent on the empty space between molecules. That means that there is an exponential relationship between the free volume available between the molecules and the change of the viscosity. Relating these two expressions and mathematically working them ends up with a theory that can be coupled into an equation of a state, because it depends on thermodynamic properties: the density, the temperature, and the pressure, apart from the molecular weight and some specific molecular viscosity parameters that had to be fitted to viscosity data. Now I'm just going to highlight some of the applications, and I want to talk about two main applications related to greenhouse gas capture, as I mentioned at the beginning. The reduction of greenhouse gas emissions into the atmosphere has become a priority for most governments, as I was mentioning in the beginning of the talk. And here, I just want to say that it is not only a matter of reducing the amount of carbon dioxide, but also reducing the amount of other many gases that are impacting on the global warming potential, such as, for instance, the fluorinated gases that we all have in the refrigerators and air conditioning. Here, I'm just showing one of the typical images that you can see on the increase of the global temperature anomaly with the years. And here I'm just highlighting that there are many substances such as refrigerants that have a strong impact, and they also have to be reduced. Let's focus first on CO2. Nowadays, there are, of course, many different CO2 capture units based on amines. Our question is, can we improve this technology using Diplotactic solvents that avoid losing solvent in the process because of the negligible vapor pressure, and having solvents that have a very, very low environmental impact? Are we capable to design a CO2 unit capture based on the performance of different performance indicators on this? Here we did a first study based on 3 hydrogen bond acceptors, 3 salts, two ammonium salts based on chloride and bromide, and also the choline chloride as the most famous salt, and different hydrogen bond donors, 2 carboxylic acid, levulinic and lactic acid, and 2 glycols, ethylene glycol and glycerol. So the first question is that, can we find an appropriate thermodynamic model to describe the behavior of this? Here we take an example of a simpler death. Tetracrylammonium salts are easier to model than choline chloride. Here we have tetracrylammonium chloride with tetraethylene glycol. So the question is, should we model this as one compound? If we model the mixture as one compound, we will have an easy model, but we will have an M that will depend on the composition. We try to keep constant the diameter and the dispersive energy. We try to keep constant the possible association values of the different association sites. We try to correlate the only changing parameter with the molecular weight. And let's compare this with the 2-compound approach, where we have a model for our salt and a model for our glycol, which is a more realistic idea, because we will have just one set of parameters for each one of the 2 compounds, and this will be treated as a mixture. Here we have the results for the 1-compound strategy. Here we can see, as mentioned, that all these 4 parameters are kept constant for simplicity, and M is changing with the amount of salt molecules added in the system, the ammonium salts added in the system, the amount of moles. All these numbers represent the ratio between the 2 compounds, 2, 1, 3, 1, 4, 1. And here we can see a density temperature diagram for the 4 systems. Symbols represent experimental data, lines represent soft calculations. They are very good, but we have to think that we have just a line here. Here is the 2-compound strategy. Now we have a single set of parameters for this molecule. And now we have, of course, a single set of parameters for, I said before, tetraethylene glycol, sorry, it was 3-ethylene glycol. And now you can see the figure. The results are of the same order. There is almost no difference. As far as this is a better description of the system, we prefer using a 2-compound approach, because this will help us to get a better understanding when we move towards mixtures with other compounds. Then, as mentioned, the second point is, as far as we are going for the most rigorous 2-compounds approach, or individual component model, let's call it as you wish, we have to identify the main interactions. Here, in this case, for this ammonium salt, tetrabutyl ammonium salt, we have used COSMO-RS to study the charge distribution and decide an appropriate sub-molecular model. For this type of tetrabutyl ammonium salts, it is quite clear that there are 2 main areas where the charges are localized. So it is quite easy to identify two main sites in the system. For the case of other molecules, such as levulinic or lactic acid, ethylene glycol, and glycerol, the discussion is more open. But as a first approach, we have given two additional associating sites to this molecule. As thought, as mentioned, there is a discussion where different options, more complex, have already been studied for these molecules. Now, just to show how important it is to have a set of consistent parameters, I just want to highlight here different salts. Tetra-ammonium salt, where we are changing the anion, bromide or chloride, or we are changing the chain of the cation, the chain of the alkyl length of the cation, ethyl, propyl, butyl. Here you can see first that as far as all salts are relatively similar, including the differences between bromide and chloride, all association sites are kept constant. Also, for bromide, all the dispersive energy values are kept constant, and for chloride, the same is done, because most interactions depend on the strength of the anion. Also, in terms of the cation, we can see that tetraethylammonium, when the cation is the same, the segment diameter is also the same for ethyl and butyl. And finally, we can see, if we see the representation of the chain length, how it can be also correlated with the molecular weight when we are increasing the molecular weight, when we are increasing the alkyl chain length of the cation. This information is very valuable because it allows us to transfer these values among the salts. If we want to see what would be the parameters of other salts, we can transfer those parameters by building these correlations and transferring these values. However, for choline chloride, the results are not so easy to model. We can see that choline chloride has many different interactions. I mentioned that in the previous slide when I talk about the work of Dr. Hunt. Okay, so here we can, just for choline chloride, not urea, just choline chloride, identify 5 different strong interactions. Two of them for the hydroxyl group at the end of the tail. Another 2 considering the nitrogen and chloride, and a 5th one considering these 3 possible hydrogens that can join hydrogen bonded chloride atom, as I mentioned in the previous slide. We consider just one of them at the same time, so a total of 5 sites were used. The association values from hydroxyl were transferred from those of ethanol, and the association values of nitrogen and chloride were transferred from the previous ammonium salts. At the end, this site was also calculated using specific rules based on the interaction with chloride. This means that only the 3 remaining M, sigma, and epsilon parameters were fitted to data. However, considering the complexity of choline chloride, it was decided to use a mixture with ethylene glycol where many density data was used. This was a work done with Emmanuel Crespo and Professor Joao Coutinho, where in their group, they have a lot of data of density at different pressures. So not only atmospheric pressure, but also high pressure data was used. And an additional constraint was included, the eutectic data included in the fitting. That means the solid liquid equilibrium line was used to estimate the activity coefficient. So to estimate the molecular parameters that were providing the right activity coefficient. In this particular case, it is important to mention that choline chloride exhibits a solid-solid transition that must be included if one wants to obtain a good description of the solid-liquid equilibrium line. As a result, we can see here the pressure density diagram at many different temperatures, and the description of the soft model is very good, going from very low atmospheric pressures till extremely high pressures. And also we can see how the blue line, which represents the soft calculation, including the solid-solid transition line, is well fitted to the eutectic data. Once we have this information, it is possible to calculate other diplotactic solvents, such as choline chloride with glycerol. And the results are shown here, fitted to high pressure data. Here we can see that we have already the calculation of, the data for choline chloride, the data for glycerol had been previously obtained, and here we obtain our calculations. Once we have done that, we proceed to our study. The study was related to CO2. Remember that we wanted to design a CO2 capture unit. So the first thing we need to do is we provide a model for carbon dioxide, which is a very well-established model, including explicitly the quadruple moment of CO2. This is a model that has been tested in many previous publications. And then we proceed to describe the ternary system between CO2 and the two compounds forming the different diplotactic solvents. These systems are fitted to available ternary data because binary parameters are needed. Okay, binary parameters are needed to describe the interaction between CO2 and the two compounds. However, it is important to mention that once a binary parameter is established, this is kept constant and transferred to the rest of systems. Once the symbols are experimental data and the lines are self-calculations, once the solubility of CO2 is adequately described by the whole system, as you can see here, we have different ammonium salts. Here we have also choline chloride salts. We proceed to do our predictions. Here, the calculations are done at different temperatures, 313, 308. It depends, of course, on the availability of data. Now, once we have the fitted model, we go to, for instance, a working temperature of 25 Celsius, which can be used in our absorption column. And we compare the performance of all diplotactic solvents. This is done using SoftSaft. And here we can see the CO2 loading capacity to absorb a mole of CO2 per mole of this. Of course, we need to keep the pressure as low as possible. So the best diplotactic solvent would be the corresponding to the blue line, TBA-Cl with lactic acid, followed by TBA-Br levulinic acid at a proportion of 1:3. If we do a comparison between all diplotactic solvents in terms of CO2 loading and in terms of solvent consumed, we can see that the CO2 loading, okay, is increasing here for the TBA-Cl as expected, as mentioned here. This is the highest CO2 loading, and these lines indicate the amount of solvent consumed. The difference between the two bars and the two lines correspond to two different cases, where the absorption is 1,000 kilopascals or 25,000 kilopascals. We can see that capturing 1 ton of CO2 would require 37.6 tons of solvent at 1,000 kilopascals, or 15.4 at 25 kilopascals. This is not good compared to amines performance, which require far less amount of solvent. However, if we check what does it happen in the regeneration state when we recover the solvent, we calculate the enthalpy of desorption based on SAF calculations. And now we can see that the enthalpy of desorption of these molecules ranges between 10 and 18 kilojoules mole, which is 4 times better than the best amine. This means that these molecules can regenerate very easily, and it would be great if we could improve a little bit the loading capacity, because there is a lot of margin to gain in the regeneration stage. Still here, the best solvent remains to be TBACl lactic acid. However, we cannot stop here. We need to check what does it happen with the transport properties. And here we perform predictions of the viscosity and diffusivity of these compounds. Now, when doing these calculations, we realize that the best solvent in terms of thermodynamic properties became the highest viscosity solvent in terms of transport properties, having a high viscosity and a low diffusivity. This absolutely prevents the use of this solvent as a CO2 capture solvent, unless we modify this with the addition of water of another solvent which could decrease the viscosity. But this is another story. I'm highlighting this because it is important to put all properties before saying what is the best compound for a particular application. The summary is shown here. The enthalpy of desorption and the working capacity is shown, and the round circles represent the mass transfer capacity. Here we can see that our best solvents, particularly this one, because they are in the high working capacity and low desorption, they have a very low capacity for mass transfer. This would be maybe the best option right now, but still, the conclusion that we can get here is that none of the compounds studied would be effective to substitute amines. And I just wanted to put this example, not because this is not the success of a successful story, but this is an interesting story to see how computational modeling can help to provide responses. Of course, other options can be studied, and they are already under study. The other example I wanted to mention is related to fluorinated gases. And this study is done in the context of an European project, which we are currently finishing, related to the reduction of fluorinated gases in the Sudoe, this is Southwest Europe, using key enabling technologies. We are studying new ways to recover fluorinated gases to avoid sending them to be incinerated. So the idea is, can we recover and separate blends of fluorinated gases that are currently being incinerated? The simulation results that were performed by co-workers demonstrated that when we fluorinate the alkyl chain of ionic liquids, 3 nanosegregated domains appear: a polar, a non-polar, and a fluorinated domain. And this automatically increases the solubilization power of these molecules. The idea is that if we can also fluorinate diplotactic solvents, they would probably become attractive to become good solvents for refrigerants that have also a lot of fluorine atoms. In this regard, we did a first study using a simple salt, amine chloride, with two carboxylic acids that were fluorinated. We can see them here. We use the Avogadro software to study the charge distribution. And we provided a one dual site for amine chloride based on the strong sphericity of the chloride anion. This is a model that we have already tested in previous applications. And a three association site for the acid, based also on several studies that suggested that more than one associating site was necessary to model the reality in the hydrogen bonding of carboxylic acids when mixed with other molecules that have also hydrogen bonds. The results were fitted to mixture data of diplotactic solvents. Here we can see the results of a diplotactic solvent based on M-perfluoropentanoic acid, amine chloride with M-perfluoropentanoic acid. Here we can see that the density at three different proportions was very well described. Remember, all the time, Simon's experimental data lines are self-calculations, and here we have also the calculation of the pure, in this case, already ionic liquid, because it starts being liquid at this temperature, which was very well described also. And here we have a description of the viscosity, which was also well represented. Then we perform, we describe our refrigerant, which is this molecule. This is a very common refrigerant that you will find in your air conditioners and many other equipment, with representing the polarity of the molecule, in this case, using two associating sites. And then we perform a strategy for the parametrization. From one side, the DES had already been fitted in the previous slide. The acid refrigerant, which is this one, the acid refrigerant interaction, was predicted. Predicted means that a value of 1 was used, and the remaining salt refrigerant interaction was fitted to experimental data. These are the two binary parameters related to energy and size, constant for all ratios. And here are the results obtained. Here we can see that the lines at different ratio and 30 Celsius can describe very well the complexity of the system treated as a ternary mixture. However, although the modeling results are good, the solubility remains quite low compared to the equivalent ionic liquid. This is a diplotactic solvent, this is an ionic liquid. Okay, here you can see that the ionic liquid has a better solubility. So here we said, let's see what happens if we decide to modify our cation and using this anion, which has also 9 fluorinated ionic liquids. We kept constant the same carboxylic acid, and then we perform a new calculation for our diplotactic solvent based on the association parameters that were transferred from the equivalent ionic liquid. We use a three-site model based on Avogadro software charge distribution calculations and previous experience. And we describe once again the pure diplotactic solvent, getting very good results using a single set of parameters. Then we decided to repeat the calculation where again the only parameter fitted were the refrigerant salt interactions, this new salt with the refrigerant, because the rest were already transferred from the previous calculation. Now we got very promising results, and as you can see, compared to the original calculation, to the original ionic liquid, we have at least two ratios that are better, that are providing better results in terms of solubility. So we are obtaining higher solubility. Finally, we said, what does it happen if we keep increasing the the fluorine atoms, but we move back to our amine chloride? If we modify again the cation, but we increase the amount of fluorine atoms, if we do that, we still construct an effective model for comparison. We still obtain good results for our DES pure description. And then moving towards the comparison, we can see that our new Diplotactic solvent is slightly worse than our previous Diplotactic solvent. Let's call them A and E to make things easier. The most important thing is that the differences are not very big, so maybe both of them can be used. But from a modeling point of view, I am insisting in the fact that only the refrigerant salt interactions are being fitted, while the rest are transferred or set to 1. And still, these fitting parameters are very close each other and very close to unity, very close to 1. So in general, we can see that a coarse-grained approach is capable to describe quite well the effect of these systems in gas solubility. From a more experimental point of view, we could say that imidazolium seems to have a negative effect compared to the ammonium cation. The idea of using amine was try to decrease the viscosity. Finally, the next steps working right now is to evaluate the solubility for other fluorinated gases in order to evaluate the selectivity between different compounds. These are just preliminary results for both of these ionic liquids for the 3 ratios using a different refrigerant, which is R32, another very common refrigerant. You can see that the strategy of parametrization remains the same all the time, and the results are quite good, even though there is some deterioration at the 1-2 ratio. Still with that, the transferability of the parameters allows us a qualitative description of these systems to evaluate the selectivity from a predictive calculation using SAT. In this case, we are checking the capacity to separate these 3 compounds. The one that you saw right now, R32 and R134A, corresponds to the blue atom. And here you can see the 6 DEX combinations, changing the ratio using the 2 different DEX. We can see that this one, the 1-2, even though the absorption is slightly lower, the selectivity is quite high, reaching a value of 2, becoming a promising option for fluorinated gases, selectivity, and separation. I just want to finish my presentation just saying that I was intending to highlight that these are a group of multiple mixture combinations. We cannot see them as pure compounds, and we need to understand them from mixture point of view, and that it is a key issue to get a clue on their interactions for an ad hoc design. Computational modeling offers a wide variety of options, and in particular, SAP can provide a balanced equilibrium between physical concepts and practical applications. However, it is necessary to include key physical information, which can be done from molecular simulations, Cosmo-RS calculations, and DFT on quantum chemistry methods. Finally, I just show a couple of practical applications where I try to highlight how computational models can be used to an industrial challenge, such as the new design of greenhouse gas capture units. Just to finish, I would like to say that we are still at the beginning of understanding the behavior of these molecules. And here I pose questions for further discussion. We need to understand how to integrate properties such as viscosity and diffusivity, and I showed a little bit how to do that, but also conductivity, pH, etc. There is a discussion on the potentially glassy nature of death and how these glassy dynamics can correlate with the physicochemical properties. And here I think that molecular dynamics can play a very important role. The effect of hydrogen bonding. We need to identify this ionic, non-ionic bonds balance and understand that not all hydrogen bonds are equal. We also need to study properties of the non-eutectic compositions and clearly identify where the liquid, the system is liquid in operating conditions. And finally, I just want to open a new door saying that it is very promising to combine thermodynamic models with machine learning, which can help in understanding the behavior of these molecules and providing a different view. Finally, I just want to say that we need to understand these mechanisms to facilitate another design for these mixtures. I just want to thank you. Funding received from different projects, Project Gas for F-Gas, and also funded by the European Union, and also projects from the Spanish Ministry of Science and Innovation. And also, I would like to thank you, some of the co-workers that I have been worked with during all my career. You can see the pictures here, and I'm forgetting many people. And in particular, and now I would like to thank the co-workers that are currently don't work on death modeling, PhD students, Carlos Alba, Ismail Al-Hatipe, Manuel Crespo, Daniel Jove, and also master student Merve Gosdiner, who has performed the latest calculations I have shown. And of course, to Professor Lourdes Vega, who is was my advisor and who is a strong collaborator in this area and many others. Thank you very much for your attention, and I hope that you enjoyed the presentation.
Thank you so much, Professor Llovell. We are now open to questions. If you want to ask one, you can feel free to raise your hand using one of the atoms or the Zoom tools. You can also write questions on the chat. And I would also like to remember that our YouTube viewers can also ask questions using the YouTube chat. So who wants to be the first one? You can go ahead, Professor Gobbins.
Yeah, very nice talk, Felix. I wanted to ask you about other properties in the liquid phase of these mixtures. So in the liquid phase, we know that if you have a strong attraction between the unlike molecules, you get very often a negative departure from Raoult's law. You can get a negative azeotrope, as you showed. You can also, in some cases, get closed solubility loops on the temperature pressure diagram. Temperature composition diagram. Mm-hmm. And a lot of work was done by the Jackson Galindo group at Imperial College on these kind of mixtures. So I wondered if in your mixtures, your DES mixtures, you also see these phenomena in the liquid phase in some cases.
Okay, thank you, Professor Gavin. It's a pleasure to greet you and to see you here. We still did not observe closed loop miscibilities in the calculations that we perform. Although it must be mentioned that most of the calculations that we have done until now were related to applications on gas solubility. There are other type of applications where liquid-liquid demixture is observed. And in these cases, it is mostly possible that closed loop formation appears. Also, I cannot confirm that because maybe there have been anything published experimentally. I don't know, because this is a very dynamic field. but I still did not see anything related to this. But considering the thermodynamics behind those systems, there should be nothing that prevents the formation of this type of interactions, this type of systems.
Yeah, it would be interesting if somebody could look at these mixtures with strong unlike pair interactions and try to, map out roughly what molecular properties you would need to observe, say, closed loops as opposed to DES or both. And I presume that could be done with SAFT, I imagine.
Yeah, I mean, of course, as I try to highlight in the presentation, it's very important to have a reliable model, to have a validated model. That's why I insist so much in that it is very important to check and recheck the parameterization, because parameterizing 5 parameters to a line is not enough, or at least it's not enough to assure that you will get something reliable when you are moving to systems that are so complex as the ones you are highlighting. But that said, it would be possible to try to check, I don't know, by increasing the chain length of one of the two systems in the mixture, or for instance, trying to increase the asymmetry of the system to see if a liquid-liquid admixture and a closed loop asymmetry would occur or would be predicted by an equation such as that.
Yeah, thank you.
Thank you to you, Professor Gamin.
Professor Silvana wants to ask a question. You can go ahead.
Okay. Hi, Felix. Congratulations, very good talk, very interesting things. But I have 2 questions, actually. One is about the capturing fluorinated gases with ionic liquids that they are fluorinated. How stable are these? Okay, they are not volatiles. I do understand that. But are they stable? It's not possible that at the end, more fluorine are going in the environment. The second thing is about the calculations on desorption energy. I do not understand very quickly for me, the desorption energy you calculate with the vapor pressure, the derivation of vapor pressure with temperature. But the thing is, vapor pressure of CO2 in the solution.
Okay, I will try.
What vapor pressure are you using here?
Basically, as far as you do not have death in the mixture, the vapor pressure of the CO2 coincides with the. I mean, you don't have death in the vapor phase, because it's basically 0. Okay, so yes, you can use the vapor pressure of your system as the vapor pressure of CO2, because basically you only have CO2 in your vapor phase.
Okay, it's just okay. Is the pressure of CO2 in the mix?
Yes.
Just I was thinking about the poor vapor pressure, and it was something strange for me. Okay, I did understand.
And concerning your first question, well, thank you very much, Silvana. It was really a pleasure, as I mentioned before, to greet you. Concerning you, I'm not maybe the expert on the experimental side, so this is a question that maybe my colleagues from Lisbon could respond better than me. But as far as I understood, all the DES and also ionic liquids, I just showed the results of the ionic liquids because I needed to focus on something. But we also have on DES, but we also have results on fluorinated ionic liquids. All of them are stable because they have been used and they have been synthesized there in Lisbon, and they have not experienced stability problems. But compared to what compared to others, are they less stable? I cannot respond to that question to you. Okay, I'm sorry, but I'm not sure. I'm not sure on that. Okay, I mean, I told you.
Maybe they should test it. How stable is?
Yeah,
I mean, because you always have a spill or.
Okay.
In the end, I mean, you have to see all the process.
Of course. No, I agree with you. I mean, and the first question that comes to my mind is, what about the viscosity? Okay, because this is the first question that comes to my mind when I see those big molecules. Okay, but still, in terms, for me there are three basic items. One of them is mass transfer, as I mentioned, viscosity, of course, a part of solubility. Yeah, another one is toxicity, which is basic. And the third one is stability, as you mentioned. Okay, so you need something that has to be you don't have to have mass transfer issues. You need something that is not toxic, and you need something that is stable, and also you need something that is not very expensive. Okay, so you need absolutely everything. Okay, so I know that many different tests have been done to find a right combination. It's not a, I mean, of course, here I do the long story very short, and I just say, yeah, and then we change this by this and magic. Well, it's not exactly like this. There is, of course, lots of fails before these combinations. The combinations that are shown here, they are pretty stable and let's say not excessively toxic. Okay, but again, for further detail, I should ask my colleagues from Lisbon.
Okay, thank you, Félix.
Does someone have another question?
I have one. Félix, thank you for the presentation. I saw that you like to use free volume of viscosity calculation. And we are seeing now in literature a lot of work on entropy scaling. I wonder how you compare with this new approach. And the other question is what's the dependence of the parameter with composition in a mixer?
Okay, so
how are these methods compared to the entropy scaling?
So sorry. So your second question is related to your first question. So you talk about
just a question, but if you compare both, I think
okay. Okay. Thank you. Well, this is very good question. Thank you very much, and also again thank you for the invitation. I have been shown the results with free volume theory because at some point, I would say 8 years ago, with Professor Lourdes Vega, we decided to work on this theory. We did a study of the different options, and comparing to the available options, we thought that this was the most physical one in terms of understanding what's going on behind. Then entropy scaling appeared in recent years, and I would say that both of them are reliable. I really like a lot entropy scaling approach because it's based on a property, a thermodynamic property that is the residual entropy. So as far as you have an equation that is also capable to describe enthalpies, entropies, and so on, you have a direct description of the viscosity. So I would say that for me it would be also an excellent option, and I don't discard the possibility to compare both. I never did a study comparing both, so putting both of them and trying to do a fair comparison. I can say that free volume theory is a good methodology in terms of first of all seeing very clearly the relation that there is between density and viscosity, which is very helpful. And also, for me, from my perspective, 2 of the 3 parameters, the barrier energy to that the molecule needs to diffuse with another molecule, and the free volume overlap are very, very, very related to the physics of the compound. And from my opinion, at some point, they could be related to the sub-stuff energy parameter, and I mean to the sub-stuff molecular parameters. Okay, there is a third one which is less clear, and for me this is a drawback of the equation, which is called the correlation length, because this L comes from the combination of two additional compounds that are combined in one. Then there is not a clear pattern for this one, which at the end represents that you always have to fit this, and you have not a clear idea of what you are going to get. We got very, very good results for systems up to polymeric systems. And we also got very good results for systems that are complex, such as refrigerants and hydrogen bonding mixtures. In terms of mixtures, there is a long discussion in terms of mixing rules. There is no clear agreement on mixing rules. We did a study where we tried up to 6 different mixing rules in one, well, before publishing a paper. And at the end, we found out that when you were getting better results with one system, you were getting worse results with another system. So at the end, we end up by going towards the simplest mixing rules that were possible, as far as we were not clearly improving the system by complicating, let's say, the mixing rules. So I think there is still a gap there. And if you want a good description using the free volume theory, I strongly recommend, and we do that commonly, what we call the spider web approach, which is, let's say, instead of fitting the compounds individually, trying to get, let's say, 5, 6, 7 compounds with viscosity data and try to fit the parameters of all of them at the same time. This seems to be more robust. If I were at the right now, I mean, if I were starting working on viscosity, I would say that, I mean, possibly I would explore entropy scaling as a possibility, because I think that for mixture calculations, as far as you are describing the entropy of mixture properly, it might be, and I put this in brackets because I never tested this, it might be a little bit more predictive.
That's my feeling as well.
I think that I always said, and I think that sometimes we are missing this in this when we are working, that sometimes people ask me, oh, you are working with this equation or with that equation, and I'm saying, no, I'm working with science, or trying to work with science. And I think that we all need to be critics and to analyze what are the advantages and the drawbacks of all the methodologies, because no method is perfect. And we are all the time doing approximations. As I mentioned before, FACT is very good. Yes, it's fantastic. But this is also a coarse grain approach, which has many limitations. If you go to the physics behind FACT, you can always see these limitations. So at the end, we need to know what is the tool that we are working with, and see where we can, until where we can arrive.
Thanks.
You're welcome.
We have a question on the chat by Virgin Land. He said, excellent presentation, Professor Fèlix. My question is, what kind of force field, that is the functional form, by molecular dynamics was used to model this, considering the van der Waals parameters estimated by your group, and how good is the prediction of the CO2 solubility with this?
Okay, well, thank you very much for your question. Well, in this case, I showed some results at the beginning of the presentation, or the middle of the presentation, on molecular simulations done by some collaborators. But the results that they have presented in the 2 applications that I have shown are done with SAFT. SAFT does not include molecular dynamic simulation. So we are not using a force field because we are not performing molecular dynamics in the study of this death. What we are doing is we are using Cosmo-RS to analyze the Diplotactic solvent in terms of charge distribution or any other type of tool, similar tool. And then once we have this, we also check molecular simulation papers that have been published by other authors, and then we propose a molecular model. That said, we are now also doing trying to do some molecular simulations, but we have still not started with that. We are finishing some molecular simulations of these fluorinated gases, and then we will move on to that. So I can unfortunately not respond to your question because, as I said, the calculations that I have shown that were performed by me and my coworkers were done with SAFT. So the estimation of the van der Waals parameter in SAFT is done by fitting to experimental liquid density in most cases, and in some particular cases, as I mentioned, also to eutectic data if necessary. So this is the way we do that, always checking that the model agrees with the interactions identified either by the charge distribution analysis or by molecular dynamics papers published by other authors.
Okay. Do we have another question? I don't think so. So I think it's time to wrap it up. I would like to thank you again, Professor Llovell, for being here and for the presentation. And now we are headed to the final announcements.